In this video, we're going to do an example of a large sample hypothesis test, and I'll read the problem to you. An admissions officer at a university claims that the average incoming high school GPA for current applicants is greater than 3.5. To verify the claim, you will take a random sample of 64 application packages and you find a mean GPA of 3.57. Historically, you know that the variance in the GPA is 0.23. Do you believe the admissions officer's claim? What we need to do first is set up our null and alternative hypothesis. So we're making a claim about a population mean. In this case, we want to verify that the mean is greater than 3.5. The null, which has to have the equality, then would be less than or equal to 3.5. We're not given an alpha. Again, a typical value is 0.05, so we'll use that. Test statistic that we're going to use is the sample mean, and we'll need to know its distribution. Since our sample size is greater than 30, we can use the central limit theorem, and that implies that y bar will be normal, approximately normal, with parameter mu, standard deviation sigma over square root of n to square root of 64. In this case, we know that sigma squared is 0.23. That's given. If it wasn't given, we'd have to use a sample standard deviation. Now we need to calculate our rejection region. In this case, that's the probability that we reject. So that's the probability y bar is greater than k. Why greater? Because to reject, we're going to have to be greater. That's what's in the alternative hypothesis. Given that the null is true, under the null, mu is equal to 3.5. And we want that to equal alpha. A couple things to note. So why do we have equality in the null? That allows us to go back and say, okay, now I know the distribution of y bar. It's approximately normal with mean 3.5. That came from the null. Standard dev 0.23 over 64. Now I can calculate this probability. This probability then is the probability, I gotta find k, such that the probability that y bar is greater than k, given that mu is 3.5 equals 0.05. I'm going to use R to do this calculation. The command in R is a quantile called qnorm. My k is qnorm. I need the area to the left. If the area to the right is 0.05, the area to the left is 0.95. The mean for the normal, 3.5. And the standard dev 0.23 over 64. I need to find that k value. I'll go to R. I need qnorm 0.95, 3.5, and the square root of 0.23 over 64. Looks like it's 3.60 after I round, if I round to 2 decimal places. That's my decision criteria. Now I look at my actual sample mean. I'm going to use a lowercase to designate it as a sample mean. That was 3.57, which is less than my k. 3.60. It means I fail to reject. Another way you may see this, and this is why it's called a z-test, is instead of doing the calculations the way we did, they'll look at a z-value, which is y bar minus mu under the null over the standard dev. This gives you the number of standard devs that y bar is away from the null mean. In this case, this would be 3.57 minus 3.5 all over square root of 0.23 over 64. If you do the calculations for this, that is 1.168. And we would compare that with just Q norm of 0.95. In this case is equal to 1.645. So it's comparing the number of standard deviations. In this case, 1.16 is less than 1.64, and again, we failed to reject. Final thing, we need to write our conclusion using a significance level. .05, I'm telling the reader what I set my probability of type 1 error at. The evidence, so I'm telling the reader that this is empirically based, it's based on data. The evidence fails to support, so I fail to reject the admissions officer's claim. So it fails to support the admission officer's claim that the mean GPA of incoming students is greater than 3.5. Has all the elements that we require. Significance level, empirically based, context of the problem. That being the mean GPA. In our decision, we failed to reject. And that's an example of a large sample hypothesis test.